Hello everyone, welcome to Thursday morning at the University of Exeter. My name is Prof. Vukusic, I'm a Professor of Physics and I'm Associate Dean for Education in the College of Engineering, Mathematics and Physical Sciences. It's a great pleasure to be with you this morning, to be live on Facebook, and I hope you'll enjoy following me around this third year lab to just sample a few things that I find pretty interesting and which my kids really like and which many students really like too. So the first thing I'd like to turn to here is this plate. And this little experiment that we're going to do is referred to as the Chladni plates, or a Chladni single plate at the moment. Ernst Chladni was a 19th century German acoustic experimental engineer, and he did some really interesting things with vibrating systems. Now, vibrating systems are at the heart of so many physics, engineering, technology applications and devices and concepts that we just want to understand that a little bit. So the level we're going to be at for the next 25 minutes is all over the place. It's going to be some school kid stuff, some advanced PhD stuff, some intermediate stuff. And so if I am talking too slow, then just have a cup of tea. If I'm going too fast, then just send a little email or a little message in because colleagues here in the room will be telling me to slow down if I'm going too fast. Anyway, so let's have a look first of all at how this plate works and what really interesting little concept comes about. So first, if you're not familiar with a loudspeaker or with a vibrating plate, let's take a look at that. We can point the camera over here at this loudspeaker, which is connected up to a signal generator. Just have a little look at the signal generator. And at the moment, it is, when we turn it on, it is vibrating or sending a signal, a pulse, at 1 pulse every second. So a hertz is per second. And we can dial it up, and that's 5 pulses a second, and then that is 10 pulses per second. So let's go back to 1, and if you go back to the speaker, can you zoom in and see the movement here? So that is a 1 pulse per second. Now, that's fine. Our ears can't really hear 1 hertz. But what it can hear is sort of about 20 hertz upwards. So as we start to dial up this frequency, the signal that's making this speaker move, what we're going to see is it start to move faster and faster and faster, and then it'll be beyond our flicker fusion frequency. So let's go up to 10. If you can just show 10 on the screen. And have a look over here again. So now it is really moving, but it's still not a proper sound yet. Let's go up to 20 hertz. And now I'll try to speak a bit louder because we've got a lot of noise going on. So now you can see the little grains of sound. Can you just have a look at the little grains of sound? You can see those okay? Fantastic. Right, let's go up to, I don't know, 100 hertz, and we'll see the sort of sound that we hear. So back to there, please. And back to this. The grains of sound are jumping all over the speaker, but we can't see it move anymore because it's moving so quickly. Right, we'll stop. So back to me if we can. Awesome. So that's basically how a speaker works. And that's how this plate here is going to be working as well. It's going to be vibrating up and down. So let's go to the plate. But before we do, let's change the speaker driver to the plate driver, and we'll go back to 1. Just so we know what we're doing. 1 hertz. Okay, so first of all, what I want to do, I want to make this, or we want to make this plate vibrate. And we can give it a whack, and that plate's vibrating, and the frequency at which it's vibrating, or the strongest frequency, is what we're hearing. I don't know if anyone has perfect pitch. I don't, so I could say that's a C or a D. Tom, do you have perfect? No, no one in the room has perfect pitch, but that is a note, and it comes about because the plate's vibrating. Now what we could try to do, if this bow were greased up, or whatever the appropriate word is, I could try to pull it along here, and that would make the plate vibrate too. Not a great job, although there's a bit of a pitch, not a very loud one. Ah, that was better. I've got to press harder then. How about if I hold an edge? Yeah. See, the trouble is, if I hold this down, then what's happening? I'm stopping the plate from vibrating in a certain way, and we don't want to do that. All it's got at the moment All it's got at the moment is a pin through the middle holding it. Let's put it back on here. And this, by the way, is a vibrating unit that is now plugged in to our signal generator. So let's have a look. See if we can get a vibration going. Oh, no. I'm not a bowman, not a musician, so let's go technical. Let's go technological. So now what we're going to do, rather than my pretty poor attempt at playing this musical plate, what we'll do is try to oscillate it. Do the same as we did for the loudspeaker and make this pin in the middle go up and down, up and down. Now you'll know that this has a thickness and it has a mass, it has an inertia. And so while this is going up and down, what that's doing, it's sending out a little amplitude wave outwards from the middle. And that's going to hit all corners and all edges. And what happens there, really interestingly, is that it reflects back. But this keeps sending out waves outwards, and you get the reflection back. And before you know it, you've got a wave going out and a wave going back, and they will add constructively or destructively to give us what should be a pattern. We'll come on to a pattern in a second. So let's turn this on. And if we can look back at the plate, I'm hoping you can hear this as well. Can you see the vibration? Awesome. So that's, we're not hearing a sound. We're hearing a pick, a ping when the pin reaches its end of movement. But let's go right up to 100 hertz. Right. So I'm going to have to get a bit closer. This is now, it's vibrating, and you know it's vibrating because when I put my hands on it, it doesn't make quite so much sound. Right, so there's a note. There is a 100 hertz note. But what's really interesting now, and this is what Chladni did, he wanted to see how the waves going out from the middle and reflecting in from the edges mixed, interfered with each other. And he did that by putting a little sugar or salt or, turn it off, salt or sand in this case. So we're going to sprinkle a bit of sand all over, nice and mixed across the middle. Going to get a bit messy, and let's just see what happens. Now, in any regions that are not vibrating up and down, the sand will remain. But any regions across this plate that are doing a lot of moving, a lot of vibration up and down, the sand will slowly, the sand particles will shift away, and it should leave a pattern. And that pattern that we see depends on the frequency at which we're driving this thing. So, switch it back on. It's going to get loud as well, so I may have to shout. So there's not a lot going on there in terms of pattern, in terms of sand particles are moving around a little bit. Let's increase the frequency. Oh, we've just done some harmonic movement there. Let's cut it down and move like this. Ah. So we now have hit some sort of resonance. You can see that the middle bit is moving up and down a lot, and all the sand particles are moving away from that. It's a bit tilted as well. Let's see if we can get this tilted to one side. Let's do an ad hoc repair. Should have sorted this out early. And let's stop it. Right, we can kind of see, notwithstanding the tilt of the surface here, we can kind of see the pattern which has emerged. So at a frequency of, quick frequency scan, 110 hertz, the vibrating pattern on the plate gives rise to this pattern, which means that this kind of circle, it's not a proper circle, but this disc is the region on the plate which is not moving very much up and down. And everywhere else it is moving a lot. So let's redistribute the sand and go right up on frequency. And just put a bit more sand here. A bit like Jamie Oliver. Or anyone abroad. He's a cook, a very rich cook in the UK. So let's go to on again, and we're going to go up. Let's bring it back to the sand. We're not going to spend too much longer on this. Let's go, I think we're going to go whenever the sound starts to jump up. Here we go, now something's happening. See what happens here. I'm going to stop there quickly. We could leave that for another few minutes and then the sound particles would slowly reveal a very intricate and very specific pattern, but you can kind of see the outline. Now that we're at a frequency of 520 hertz right there, the mode of vibration on the plate is different to that which we saw at 110 hertz. In other words, the way that the waves go out from the middle and recombine after their reflection is different. It's frequency dependent. Now, we can talk about this for hours, but we've only got another 20 minutes, 15 minutes probably. I've been yabbiting on. Let's move over back to the speaker and back to something which is really neat, which kids love, which adults love, and that is cornflower. We're back to Jamie Oliver, of course. So what we'll do is we will look at maybe mixing up. We've got 150, let's pour a little bit off. This is clean water, Tom? No, drink some. Excuse me. So we need slightly less, a bit more. About 100 mils. Let's go over here with some corn flour. Those of you who are teachers will, of course, know all about this. It might be a bit too much. We have 200. Let's put a bit back, put a bit back here. I haven't got time to pack it away. Right, so this is a liquid, and what we have with the liquid is when we put something into the surface of a liquid, of a normal Newtonian liquid, you know where I'm going with this, then it behaves in exactly the same way as a liquid behaves. In other words, the viscosity, the resistance to flow, is independent of pressure, of strain. Of stress rather. So let's mix this up a little bit. I'm not a terribly good cheese flan man, so I've probably done that in the wrong order. Nonetheless, let's have a quick look inside here. It's starting to mix. So, corn flour does not dissolve in water. It forms a suspension, and that means that the corn flour particles, the complex polymeric particles, are just dispersed throughout, but they're still particles. They don't, as I said, dissolve. Now, what does that lead to? Well, that leads to something very interesting. It will take a few more minutes to mix this up. So here is one we prepared earlier, and it's blue because we've got a little bit of blue food coloring in there. And what we wanted to do was put it on the loudspeaker and just see what it does. So before I do that, and it's going to get a bit messy here, Tom kindly provided some gloves, but I've forgotten to put them on. Here they are. And let's go back to 1 hertz. 1 hertz. So can we just confirm that's 1 hertz? And when we turn it on, right. So if we can just have a look here, there is the 1 hertz pulse. Let's pour this corn flour mix on here. All right, it's starting to flow. Everything is good. And let's see what we see. So it's already a little bit strange. There is a difference in viscosity, and that's due to the way in which it's been mixed or unmixed in the beaker when it's been standing. But it's flowing quite slowly. And I'm going to try to scrape it, but it doesn't want to be scraped. In fact, let's leave that there. Let's go to the frequency generator, and let's just increase it. Already, if you can zoom right in on this, so I'm going to try to push my finger in, and already, it's not just if we have to turn this off, I could already, so this thing is not letting me go into it. It's a non-Newtonian fluid. Now here's the secret, and here's the really neat thing that may not quite work here on the speaker, because sometimes the mixture has to be right. it reacts to stress. And the way it reacts to stress is by becoming more viscous, this particular cornflour mixture. And there's a specific name for that. I think I've forgotten the name, to be honest with you, but it is a really interesting property that displays very applicable shear viscosity properties. So let's whack this up and see if we get some solid lumps jumping out of here, and if not, stop that there. This isn't working quite, and teachers who are looking at this will probably tell me exactly what I'm doing wrong. But what is really nice is this. I'm going to see if I can put this in my hand. So you can see it flowing all over the place, and let's put it right here. So there's a bit of a kind of a geeky name for this. This name is oobleck, and the oobleck name comes from the author of Cat in the Hat, Dr. Seuss. And oobleck was the name for a particular type of rain that fell in this kingdom that Bartholomew lived in. So you can sort of see what's going on here. I am rolling this now. This is a kind of a liquid, and you can see it being rolled into a ball. Now, when I'm pressing on it, the viscosity rises, so it almost feels a bit like a solid. And then when I let it go, it disappears. Now, the physics of that, the mechanics and engineering of that is really well known. And it's to do with the way that it's not a proper liquid like water is, it's the way that it's a suspension. And when pressure is applied, water that exists between these cornflour particles gets squeezed out a little bit, and the particles themselves, these complicated long polymeric particles, overlie and get squeezed together, and then there are higher resistive forces between them. Okay, so we've got to stop that just for now. Oh, no. Tom, here's what we're going to do. Last experiment. How are we doing for time? We're good? Okay, so here is an egg. I was going to say laid by 4 of the chickens in my garden yesterday, but no, there is a date on that egg, so I bought that one. However, what we're going to try to do, normally if I were to drop this, it would hit on that point or on that point or on that point, and there'd be huge stress on one very tiny region. And that's why eggs crack, principally. The shape of the egg sometimes improves the strength. If you had a circular one, there are mechanical properties associated with this shape. But one thing that might be good to try is if we can use this non-Newtonian liquid for, all right, actually, Tom, would you mind if you could somehow transfer that, mix it up a little bit, transfer that into the bag, and then we'll come straight back to it between the other demos. Thank you, chap. And we need some more tissues. Can we go over here now? Oh, fab. Leaving hand. Oh. Right, so we're on to optics now, light and colour. This is another really interesting area for me, certainly. And I'd like just to see if I can tempt you and tease you with some of this stuff. You'll see a collection of a few butterflies here that this is really where my area of science lies. But we're looking at colour, the way colour is produced. And there's lots of interesting applications with the way colour is used, or the way it accelerates technology, communications, optical fibre. All of those things have revolutionised every area of our lives. A big question for scientists, engineers, bioscientists, all sorts of different fields is what creates a colour like that? So this is a Morpho butterfly. There are several different, well, there are 40 different species. There are 2 types of species here. This is Morpho retina. That one there is Morpho dius. And it has a very interesting property. I'll get the water again. Here is some water. What we're going to do is just have a little bit of a look. Can you pick up the reflection of light? So I might rotate this around a little bit. What do you think? Are you getting the flash there? Awesome. I will bring that back and let me demonstrate what's going on here. First of all, it's important to say that it's not a color generated through pigmentation, through some sort of chemical or dye. Pigment is the natural variant of dye, or dye is the synthetic version of pigment. And we're going to see what happens when we put a little bit of water. Here's water, here's a bit that I drank from earlier. Let's have a look at this. It's rough, the surface is rough. In fact, let me show you this. Here is a 3D printed, magnified version of what the surface of that looks like. It looks like, can you zoom into the cross section? It looks like Christmas trees. Lots of columns with branches going out to either side, but they're not really Christmas trees, they're Christmas hedges, because they run all the way up and down. This is a 20,000 times magnification of the structure that we see here. Right, so let's put a little bit of, here's an empty syringe, hopefully. I'm gonna grab a little bit of water. Right, now normally we'd think that water would wet a surface. Let's have a look at this surface here. And well, the water's not wetting. Now it's wetting, okay. But as I dropped it on there, because of the roughness of the wood, or the wax on the surface, it hasn't spread out. If we do this, then it spreads out. So that is wet. That droplet there isn't quite wet. So let's go back to the butterfly. And we're going to put a droplet of water onto the surface. And just see what happens. Ooh, doesn't want to come off. I'm going to have to get some more water. Here we go. Let's try again. Right, how close can you get to that droplet? Let's bring it close to the light as well. And what we'll do is try to get it rolling off. This is one of the reasons why, well, butterflies don't like flying in rain. But if they do get some dew or rain falling on them, they don't wet. Well, it seems to be locked, but it's not wetting, it's not spreading. Shall I just roll it off a bit? Oh, and I've picked that up on my finger. So this guy is hydrophobic. Now let's just take a look at this box here. That's some Science Museum kind of $4.99 purchase. And this is hydrophobic sand. So surfaces can be treated in such a way that they can be made hydrophobic. They can be made so they're not wet. Right, so let's empty some of this hydrophobic sand out here and drop a bit of water on there as well and see if it behaves in the same way. Yeah, okay, so there are a couple of drops. And the great thing about that is it definitely doesn't wet the surface, and as you roll it, there it's gone to the side, it rolls away from the surface, and if this were a lotus leaf or a butterfly wing, it will take and carry dirt, dust, fungus, sometimes bacteria will roll off in the water droplet as well. So technologically, super hydrophobicity, or the capacity to engineer it, is really useful. However, we veered away from this idea of colour. What I want to show you is that this is generates colour in a really special way. So I'll try to take all of this water out. I think we're squeezed dry. And we'll have a look at this now. This is a transparent vial of fluid. That's not water. Okay. If I were to drink this, I'd get pretty drunk. It is pure alcohol. I'm not going to do that, by the way. But we're going to put a bit in here. So the difference between normal water and something like alcohol is a thing called its surface tension. The surface tension of water is really high. What that means is water really likes to form bonds with itself. And so if you get a surface, like a butterfly surface or some other surface, that isn't very attractive to the water, it doesn't like it to spread, then the water will ball up. And that's the result of surface tension. Alcohol has a super low surface tension. So when you drop it on a surface, it spreads, it wets the surface. Now, if this is the structure of the butterfly, it's got lots of air gaps. Imagine this great big syringe coming down and dropping a massive balloon of alcohol on here. The alcohol will penetrate all of these gaps and it will change the way light interacts with the surface. So can you do a close up on that? Thank you very much. So let's see, and we'll need to actually get to the light. Okay, so a little bit of alcohol. At the moment the butterfly is blue. What's a good reading of colour? That's not bad. Let's do that. Right, so we're going to stay looking at that. That is green because the optical interference, there's the jargony sort of posh phrase for it, the way in which light waves interact with that structure has changed because now it's full of a different substance. Now, the good thing about alcohol in many ways is that it's volatile. That means it's got a low evaporation point. So this, before our eyes, should be evaporating. And even if I were to breathe a little bit more, you should see that the original colour is returning because the air is refilling all the gaps between the branches of those trees that I was telling you about. Now, it may just sustain a little bit while the residual alcohol is still evaporating, but we'll come back to it in a minute maybe, and that will be it. Great. So, what else have we got to do? We have got to do something pretty interesting that I would recommend kids do with a little bit of caution. Tom, how did that bag fill go? The bag is there. Oh, we're there. Yeah, let's do that. Let's jump straight back to that. Thank you very much, Tom. So here is our non-Newtonian fluid, and this is cornstarch, 1.5 cornstarch to 1 water. And we're going to go and get our egg. Wipe this a bit clean. So, I've never tried this before. And as teachers will know, always try your experiments first. This could be a big fail, right? Hopefully it won't be. And why we're demonstrating this, what we're trying to do is to show that this is a kind of liquid, non-Newtonian liquid. And the good thing about liquids is pressure on something in the liquid is equally applied across the whole surface, not just at one point. So if you go swimming and you go 2 meters below, the same pressure, more or less, is all over your body. Your head, if it's pointing up, will be at slightly lower pressure compared to your feet, but it's not that different. So let's see if we can put this egg in here. I'm going to let it sink. And we're going to, Dave, the lab owner, will just give a bit of a wave to Dave over there. Some of you might remember Dave if you graduated from this lab. Okay, so here we are. This is now going to be, and I'm going to do a bit of a jump here. Okay, this might fail, but let's try it anyway. Ready? Apple. How many in the room think we're going to retain the integrity of the egg? Got 1, 2 out of 5. How many think it's not, including the camera room? No, we've got 1 doubter. Let's see. Okay, so this egg is buried right in there, and I'm going to, how tall's the roof, Dave? The ceiling? 7 meters. 7 meters. Okay, I'm going to try to do that. Should we try? Let's start small. Let's go 3 meters, 3.5 meters. Ready? Ooh. That sounded pretty positive, and I think we've got an intact egg. Let's go even more ambitious here. That was really effective. I'm just trying to cover the whole of the egg. And are we ready? Oh, that didn't sound so good. Didn't sound so good. Yes, we will, we'll move on from that one. It worked for 3.5 meters, the 7 meters didn't quite work so well. But maybe some of the egg was exposed. You can see that there's a lovely concoction there. We're back to Jamie Oliver. Corn flour, egg, and water. There's a cake in there somewhere. Let's go back to another little demo. Tom, how are we doing for time? Fine. Okay, one of my favorites is to do with light sticks. Now we know light sticks, let's get this green one. The light sticks is an example of chemiluminescent. And most kids will have seen one at Christmas or Guy Fawkes or Thanksgiving. And inside this, hard to see, maybe if we do that, there is a glass vial, and the glass vial has one fluid. The other, outside the glass vial, but still inside the plastic, is another fluid. And when you break the vial, mix the two fluids, you get, let's go down here in the dark, you get a, in this case, green chemiluminescence. Okay. Now what we're going to do over here is just show the nature of this. Please be super, super careful of this if you are looking to try it at home in the classroom. But we're going to saw this open. And to help with that, we'll need a couple of beakers. Yeah, would you be able to bring that one over? Okay, so basically, we're going to try to take these two liquids out of these containers, thank you, and we're going to mix them ourselves. It is a bit fraught with trickiness, so let's sort that. Tom, I may borrow you again. If you could just hold this underneath this when it starts to come out. Thank you. All right. So, in fact, hold on a second. What I'm going to do is I'm going to open my brand new safety specs. Safety first, boys and girls. Okay, back to it. Slightly higher, please, Tom. Okay, so you can see the liquid A is starting to come out. I should probably as well just stay there, Tom, a second. Let's have a little play here. Right. And the vial should come out. So we'll put that one in there and we'll put this in here. Thank you, Tom. Right. So there's nothing spectacular in that. That's just a normal little, now relatively empty, albeit wet, plastic tube. We have a little bit of fluid there. Are you getting that? Awesome. However, we have a vial here that has a bit of fluid A on the outside, which we'll try just to dry off a little bit. There we go. And the question is how to break that. So please, look into my eyes, just my eyes. Do not break this with your fingers. I tried that once and it didn't end well. So the suggestion is to pop it, even though it's still wet in there with liquid A, pop it back in there and let's break it in here and then we'll drain the fluid into here. All right, so that is fluid B, let's call it. Now you know exactly what's going to happen, don't you? Everyone does. We're just going to mimic in two glass jars and then into one what happens in the original single plastic case. But it's just a bit more fun. So you can see in there that we've got the bit of the glass vial. We have liquid B, which is red in this instance, or kind of magenta red. And then, and we're going to go somewhere, come down into this little cubby hole with me. I'm going to try to get some chemiluminescence going. So at the moment they're pretty much separate, although you can see that there's a little bit of liquid A in there because it's starting to glow, it's starting to luminesce. And as we pour that down in there, we get chemiluminescence, exactly what you'd see through the tube if it was intact and you didn't saw it open. Now a lot of insects do that. A lot of insects use not chemiluminescence, it's bioluminescence. And they use it for all sorts of biological purposes, mostly communication, intraspecific, so communication with the same species, communication with other species as a warning signal, as a false attractor, those sorts of things. And what we will also look at is this idea of bioluminescence or chemiluminescence is one type of color or light production. It's light production, but colored light. Another way of producing colour is, in addition to the reflection we saw from the Morpho butterfly, is fluorescence. So all of these essences, that's a set of complicated words. Bioluminescence. Luminescence is really to do with light. If something is luminous, it's giving off a bright light. Let's look at fluorescence, which is when a substance, paper, material, pigment, whatever, absorbs a violet or an ultraviolet color, and it re-emits that energy as a green or blue sometimes or orange sometimes color. So it changes the energy conversion, which converts it converts kind of ultraviolet, usually energy, radiant energy, to more visible energy, often blue. So let's have a look at that. And to do that, we need to get a UV source. Dave, would you mind, now the sun's come out, would you mind just dropping the screens on that side, please? Thank you. The power of Greystone. So, what shall we do first? Well, first of all, I'm going to just put a little bit of moisturizer on one side of my face. I'm supposed to do this every morning, but never do it ever. We're just going to put a bit of that fluid just on there, halfway down. Let's do this kind of thing over here. You'll see what's going on in a minute, and maybe over there as well. Okay, so I'm not sure. Anyone in the room, can you see any moisturizer? Not really? Excellent. Put that back. So, if we shine white light onto something like paper. Tom, could you get just a sheet of normal white printed paper, please? That's awesome. So, when we illuminate this with paper like that, we just see normal whiteness, and it's really white. When we illuminate this DAS or Persil or whatever it was, washing powder, clothes washing powder, with white light, it just looks really white. No surprises, no dramas there. But here's what happens when we take this UV tube, let's just read the print, UV, what does it say? UV midlight. So that gives off a reasonably safe ultraviolet light. I'm going to put some glass over my eyes, and that will, if this is true glass, then that will protect my eyes from UV. But now look what happens when, might we turn the lights off, Dave, would that be right? When we shine on this. So UV is, let's turn it and close that down, we have a blue glow. So at the moment, if we're looking at what should we look at? Let's look at this thing here. We see a kind of violet glow. Already though, you're seeing that my clothes, my white shirt is glowing. Some of the stuff on my hand is glowing too. That's fluorescence. And we're going to come back over here. This is paper. Paper has a dye on it called a fluorescence whitening agent, and that takes in the ultraviolet from the sun usually, and it changes it to white, or rather to blue, which then enhances the white. Because we think that a bluey whiteness is much more clean than a normal yellowy whiteness, even though it's just come out of the same washing machine. Persil washing powder has a fluorescence agent in it. So the reason that my shirt is really glowy is because it's washed in this stuff. And you can see even though I'll incur the wrath of Dave, who owns the lab, let's just pop this on the floor and you'll see that it's glowing blue. And it's glowing blue because of the fluorescence whitening agent that we've got in it. So, back to nature a little bit. Does nature use this? We talked about a butterfly. Well, first of all, let's show you these butterflies. The morphos on top there are not fluorescing, but the Papilio zalmoxis there is fluorescing massively bright. Can you see that okay? Even though they are receiving the same type of illumination, albeit ultraviolet illumination. Now, the reason that has evolved the capacity to fluoresce is because it uses it to enhance its communication. And if we understand biological fluorescence systems with more to a greater depth, then we can actually use those things in technology. For instance, in moisturizing lotions. How's that looking? Glowing? Scary. Okay, yeah. Long time since I've been called scary. Right, let's go in the we're on the home stretch now. Tom, what is the time now?
It's 22.
22, so we've gone long. We've gone long. Let's, we're going to do 3 more minutes, 4 more minutes if everything goes well. Let's protect this and race over to this side. So, we're going to need some protection. I think I'll go with the glasses. Again, I'll go with the gloves. It's winter time in the UK, and in Exeter it's much warmer than the rest of the country, but usually. But it's still a bit chilly today. So this is H2O, liquid nitrogen. Dave, would I be all right to drop a little bit on the floor?
Yeah.
Awesome. Okay, so let's just have a look at what happens when we drop liquid nitrogen. Oh, could you come in and take a look inside here first? Fantastic. So that looks like a liquid. Well, it is a liquid, but it's liquid nitrogen. It's really cold. So dropping a little bit on the floor. And because the floor is at room temperature, and that's way above the evaporation point of liquid nitrogen, then immediately it vaporizes. Okay, so what we're going to try to do is a couple of things. We're going to have a quick look at the mechanical properties of certain things when their temperature drops. Here are a couple of flowers. I'm going to take one glove off. Here are a couple of kind of flowers. Now you will see that, anyone know the names of these flowers? No, we're clueless in the room. Please drop a line in to the Facebook message if you do. I bought these from my wife, or she bought them for herself, I can't remember. Either way, they're here today. So when you know the sort of normal property of a flower, it's squishy, it feels natural, there's a word for it, and both of these will look like that. But let's just see what happens when we dip this into liquid nitrogen. Now, you'll probably know what's going to happen. It's going to, well, let's have a look, shall we? Come and have a look as this dives in. Now, it seems to be boiling, and that's because the temperature of the flower is at room temperature. Okay, so here's the flower. Now, again, if ever, you'll know this if you deal with liquid nitrogen. Cover that up. Never touch that because that's going to be pretty cold now. But what is the texture? What has that temperature done to the physical property? This will be no surprise that the water within the flower petals has been frozen and there are ice crystals, and that makes the whole thing really, really brittle. So this is staying here and it's not going back to my wife at home because it won't be appreciated. Here is celery, right? I'm not a fan of celery myself. I probably wouldn't choose to eat it. However, let's have another look at what happens here. It'll be the same thing, but it's always a lot of fun dipping food into liquid nitrogen. It's boiling once again because we know that the temperature of the celery is, well, it's room temperature, isn't it? And now when we take this out, hardly a surprise, and I promised Dave we're going to clean this up after this session. Okay. I don't know if this will work. We didn't test it. Again, that's a big fail for me here. However, we have, let's look at the effect on batteries of low temperature and changing temperature. Now, this is pretty extreme. So we have a little motor here, and the motor has a flag, and if I connect up here, should we get in a little bit closer? If I connect this up, and by the way, this is just a regular, what is it, 9-volt battery? It's a battery, and it's reasonably new. Okay, so what I'm going to try to do is dip this battery in there while the motor's on and see if there's an effect. What we expect is that the current generated through this system, through this little circuit, should reduce because of the effect of temperature on the way that the chemicals within this battery are working. So, I'm going to boost it up, and then let's see, this may or may not work okay. There's a slight change in tone. Right, just have a listen for the pitch. Even though it's out, the whole process inside this battery isn't as efficient as it was at room temperature. And so I can certainly hear a change in pitch, which is related. And as I'm talking, you can even hear the pitch reduce, which means it's rotating less fast, which means less current is getting to it. So in other words, as expected, temperature has a big impact on how the chemical processes inside a battery take place. Chemistry is invariably temperature dependent. Right. One other thing that is temperature dependent is ice cream, and that's what we're going to finish with today. We are going to try to make some ice cream and to thank all the guys in the room and to raise a cone of ice cream to you as well. And we have the basic ingredients here. Thank you, Tom. So we have some wooden spoons for mixing. We have some cream. It's leaked a little bit of milk. We have some, my favourite, Cadbury's Flake. That's a kind of guiltless plug there. We've got a little bit of vanilla flavour because is there any other flavour than vanilla? So what do you think, Tom? We're going to just chuck everything in?
Yeah, use both bowls.
Both bowls, okay. Right, come a little bit closer there.
Inside each other.
Inside each other. Like this. Awesome. Oh yeah, awesome. Okay. So let's put. Tom, you tell me. I'm a bit new to this, so we're going to go half and half.
All the cream.
All the cream.
Okay.
Yeah. You can't beat a bit of single cream. How much milk, Tom?
Quarter of that.
Quarter of that. Okay. So here's a pint of Devon milk. And let's do that. Let's get a bit of this back to cooking somehow. We had the corn flour. Probably enough there. And sugar. Ice cream is not ice cream without sugar. How much, Tom?
Oh, about a third.
About a third. Okay, so this is silver spoon. And let's go with that. Right. So at the moment, this isn't ice cream. This is just cream and sugar and a bit of milk with a bit of vanilla flavour. And when I mix this up, if you were to taste this, well, it'll still be nice, but it just is not ice cream. The thing about ice cream is you have to, or making ice cream is you have to freeze stuff. And if I just put this whole thing, if we put this whole thing in a freezer, it would freeze and it would be a solid lump. The key is to prevent ice crystals forming. Now we have a little bit of liquid nitrogen here that is remaining from the experiments we did earlier, but we're going to use the liquid nitrogen to help us freeze the sugar and cream and milk. But at the same time, we're going to mix them pretty violently, and hopefully, if we get the pour rate right, few ice crystals will form, and we'll get ice cream. Tom, what do you think? Do you want to help with that? And I'll give it a stir. Why don't you stick the hat on too? This is Tom Stevenson, everyone. Right, we've got about 2 or 3 minutes left, and then we're going to have to clean up. Okay, have a little look inside, come inside here. Go, Tom. Keep going, this is good. Keep going. So remember, the purpose of the liquid nitrogen is to, check that out, is to freeze the thing. And all the time, as we're doing this, the liquid nitrogen is doing its freezing job, but then it's evaporating. So it's not like it's part of the ice cream. Right, we might nearly be there. Let's perhaps leave that for the moment. And we'll need some cones. Right, I haven't managed to get. Okay. It's looking a bit more like ice cream, you see that? And first cone, please. been a very great pleasure to talk with you all this morning and to share a few of these experiments. In a fun way, in a kind of crazy way. There's one for the camera lady, and one for you, Tom. If you've got any questions about what we did here today, I'll be really happy to answer them by email, on Facebook or otherwise. The team here would be really happy to answer any of the questions that you might have. Thanks ever so much for tuning in. And if you plan to visit Exeter in the near future, I hope you have an enjoyable day. And I look forward to maybe seeing you sometime soon. Bye now.